Hello everyone, my name is Aditya Tiwari. In this tutorial we cover M-way search tree. So before we start this topic, we have to know the concept of trees. Already we covered trees part in the previous tutorials like trees, binary trees, types of binary trees, and also we covered the AVL tree. We have to understand the concept and the drawback of the binary search tree which is sorted by the AVL search tree. But all the kind of tree in a binary search tree, they're having a limitation or restriction in a form of a children. At least 0 children, and any node, a root node or any internal node will produce at most 2 children only. That is a restriction inside the binary tree. AVL trees also follow the property of binary tree. That's why the AVL tree is a balanced tree but follow the property of binary tree. But now we change such kind of phenomena. We can produce more than 2 children as per the order of M in a M-way search tree. M-way search tree is a little bit better as compared to the binary tree because when we go for any kind of operation like a searching, insertion or deletion, it is quite easily and we can search any item. It will take less time as compared to the binary search tree. That's why we studied this tutorial, this topic in this tree. So a multi-way tree. M-way tree is a name, full form is a multi-way tree, is a tree that can have more than 2 children. A multi-way tree of order M. M-way tree is completely depend on the order. M is representing the how much child will be produced by the single node, either a root node, either an internal node. So M is representing the how many numbers of children will be produced by that single node. So M is a nothing else a number, or a M-way tree is one in which a tree can have a M children. Later on I will discuss what is the role of M and how we put the value of that M. So an M-way search tree, M is does nothing else a representing of the order of any tree. M-way search tree is a M-way tree in which first one, the sub point inside this one, each node has M children. Every node, I'm talking about the every node, I'm talking about the every internal as well as the root node. Each node has 2 children and M minus 1 key fields also. So in the second point, the key in each node are in ascending order. When we fix any element, any data inside the structure or in a hierarchical structure in a tree, we should to insert a node as in a ascending way. So in that way data storage will be managed by the properly way. Next point, the key is the first I children are smaller than the ith key. Suppose as I told you, every node having a 2 children, one form is a left children, another form is a right children. Left children, or we can say the left successor of any parent node, it should be a less value as compared to the next ith children. It means suppose a key producing a 2 children, first is a I1 and second is a I2. I1 is less than, all the children are less than the I2 children. Later on I will discuss in the diagram what I am telling you. So here you can understand the I1 children's are all the nodes are the less than as compared to the next coming ith children's like I2, I3 and so on. The keys in the last M minus I children are larger than the ith key. So talking about the last one, M is representing the children. The last children are larger than the ith key. Suppose the last I is representing the children node. The last item, last key node which having a right children also, and right children successor datas all are the greater than the keys data. So that's why the first I is all are the data is less than the key data, and the last I all are the data are the greater than the key data. By this diagram you can understand what I am telling you, how we insert a node, how we insert an item, or how we representing a M-way search tree in a ascending order. So by this diagram you can understand here we can insert 2 items at the root node. That is the first one is a 10 and second one is a 44. Before this M-way tree we studied already binary tree, and in the binary tree we insert only a single item. Suppose either a 10 I will insert or either a 4 or 44 I will insert. I was inserted in that tree, but we can't insert a 2 item at the root node. But this is possible in a MV search tree. We can insert 2 item or more than 2 item at the same level or the same root node. So by this approach we can obviously directly proportional to the searching or any kind of operation we can perform in a data structure. So here we insert a 2 item in a root node. The first item is a 10 and second one is a 44. By this diagram you can understand all the items, suppose 10 having a 2 keys, the first key and the second key. First key are connected as a left child or a left successor of 10 and another key as a right successor of 10. Second key as well as the left successor of 44 also. First to understand what I am telling you. So the left key of the 10, the connected item are all item are less than as compared to the internal node. Here the internal node is 10 and the left successor are items are 3 and 7. Both are the less than the key value, because here we can see 3 and 7 both are the less than the key value 10. Here the key is a 10 and 10 having a left successor or we can the left child are in the form of 3 and 7 in this tree. Now I'm talking about the next item, that is 22. 22 is greater than 10 but it is less than a 44. It should be connected in between the 10 and 44. We having a path, we having a right child of a 10 or we can say the left child of 44. So 22 should be connected by the right child of 10 or we can say the left child of 44. So here 22 will be connected in the form of a right child or we can say the right successor of 10. So again I told you, as I told you in the previous one, the I1 element 3 and 7 are 3 and 7 both are the I1 element and 22 is the I2 element. The elements 3 and 7 are less than the 22 item, as well as the parent node also. 10 is less than 44, it should be insert as before 44, not after 44. That's why I'm telling you state data should be insert in a ascending orders. So in the first level as a root node, the first is a 10, that was a 44. Now in the second level, I'm talking about the next height. Next generation is 10 producing 2 children. First is a 3 and 7 and second child is of 22. Now another one talking about the 55 and 70. Both are the greater than 10 as well as the 44. That's why it should be connected as a right child of 44. And the 55 and 70 both are connected as a right successor of 44. If you see all the item in the second level, all items are in the ascending order, like 3 and 7. After that another child is a 22 and another child is 55 and 70. All items are connected or inserted in a ascending way order. Suppose in a next, again I want to insert a new item. So again suppose a new item is 50. Here I am 50 connected. Again I check 50 is greater than 10. Again 50 is greater than 44. It should be connected to the right child of 44. Again it will check 55 and 70. 50 is less than 55. We should to connected this 50 as a left part of 55, but having some restriction, that is complete order of tree. Here the order of tree is a 3. So we can insert it only a 3 children in a single level of any item. So 55 and 70 already 2 items are connected. We can't insert a new item 50 because the space is already filled. So maximum connectivity path, that is a 3, and 3 is already covered by the 2 items. So 55, 70 are the ith item and the child are the 3s. So 50 should be connected as a left child of 55. Next item is 66 and 68, and both are again when we comparing with the root item, then the internal node, and both are the greater than 55, but both are the item are less than the 70. That's why it should be connected as a right child or rather as a right successor of 55 or a left successor of 70. That's why 66 and 68 both are connected as a right successor of 55, or we can say the left successor of 17. There is no another item in the tree, we have to connect it. If suppose any other item should become like 75 should become, so 75 it should be greater than the 44 as well as the 70 also. So we definitely connect this item 75 as a right child of 17. By the connection, we insert that item, and but after the insertion it follow the property of MV tree, because MV tree having a restriction only the order, not if we follow the order, it means we can insert any number of items inside the tree. I will tell you what is the role of M, what is the role of child. One by one we can understand the concept of MV tree. So by this diagram you can understand the overview of MV search tree. We insert as per the order, we insert any item at the root node, in the internal node, and by the smaller or greater we can insert any item inside that particular tree. Now in a binary search tree, M equal to 2, so it has one value and two subtrees. The last figure in a MV search tree of order 3. As I told you, 3 is means maximum producing child are the 3. We can't produce more than 3 children in particular order of M, where the M equal to 3 in a MV search tree. So MV search tree always follow the property of order of M. MV search trees gives the same advantages to MV trees that binary search trees gave to binary trees. Already we discussed this point when we discussing about the last tutorial in a binary search tree. That provides fast information retrieval and update as compared to binary tree. In a MV tree, when you're updating your data, when you're updating your information or retrieving your data from the memory as compared to the binary search tree, and that definitely it would take a less time. So it's an update version of a binary search tree. However, they also have the same problem that binary search tree had. They can become unbalanced. Same like kind of binary search tree. Binary search tree is a unbalanced tree. MV tree also is a unbalanced tree. This is again a drawback of MV search tree. But right now we will not discuss about the drawback. We have to go for the strength of MV search tree. But we should to know what is the drawback of MV search tree. So I am only a single drawback in MV search tree, that a tree, after we creating a tree in MV as per the order of M in MV search tree, the tree is unbalanced, which means that the construction of the tree becomes a vital importance. So in MV search tree, each subtree is also a MV search tree and follows the same rule. As per the order of M, the M is any integer value which is based on, we can identify the same rule of that particular tree. An extension of multi-way search trees of order M is a B tree or a order M. Extension of MV search tree, it means the MV search tree is a unbalanced tree. When we go for the balancing tree, we should to update the MV tree by the concept of B tree. In the next tutorial, we go for the B tree concept, how we go for the unbalanced tree to the balanced tree by the rule or the principle of the B trees. So MV tree provide you facility to insert any number of items which is order of that depend on the order of M in a MV search tree, but the only drawback is that after creating a MV search tree, the tree is maybe unbalanced. So this type of trees will be used when the data to be accessed, stored in located on secondary storage device, or secondary storage means the ROM part or the hard disk part, because they allow for large amount of data to be stored in a node. So when we insert any item in a secondary memory, or we can say the hard disk, all data should be present or connected in a form of this type of a structure in a hierarchical as well as in a linked list form also. So we easily store our data inside the secondary memory. So easily we can fetch our data or retrieve our data easily from the secondary storage devices. By this diagram, you can understand how we generate, how we create a M-way search tree. Consider the example. Here we having a table, and table having a value like C1, K1, C2, K2, C3, K3, C4, K4, C5, K5, C6, K6, C7, K7, and last one is a C8. Here all C's are representing the childs. So note down, C is representing the childs and K is representing the keys. Keys also we can say the parent. So K1 is a parent 1, K2 is a parent 2, and so on. The K7 is a parent 7. And each and every parent producing a 2 children. So maximum it producing a 2 children. So K1 producing 2 children in a form of C1 and C2, child 1 and child 2. When we go for the K2, K2 parent producing again 2 children. First one is a C2 and second one is a C3. Then K3 producing a C3 and a C4, K4 producing a C4 and a C5, K5 producing a C5 and C6, K6 producing a C6 and C7, and K7 the last key producing a children in a left successor. As a left successor is a C7 and a right successor is a C8. So in this form we can connected our childs in by the key, or we can say by the parent. Here you understand the C1 values, whatever the item you connected in a C1, it should be a less than the K1. It means all the C1 children are smaller than the K1 values. Vice versa, C2, all the nodes or we can say items are available inside the C2 are greater than the K1, but it should be less than the K2. So C2 will be lie in between a K1 and K2. K1 is also a parent of C2 and K2 is also a parent of C2. But the difference is that K1 is a key and is also called a parent. The parent value is less than as compared to C2 items, but K2 key is a greater as compared to the C2 children's. So C1 children are come first, then parent 1, that is a form of key 1, then parent 2, then second child is a C2, then we come to the K2 or the second parent. So one by one, first child, then first parent, then second child, then second parent, then third child, then third parent, and so on up to the we can generate our key structure, or we can say our M order structure. By this diagram, usually understand the concept of how we generating, how we creating, how we fix our data inside the structure. This node has the capacity to hold 7 keys and 8 children. You always remember one thing. The values of children or keys difference is that so key is 1 less than as compared to the children. Suppose here we producing 8 children, so the maximum keys are present in the structure is 7. So key minus 1 equal to children, or we can say key equal to child plus 1. Suppose key having a 5, so children value is 6. Again so on, K1 talking about the keys, or we can say parent, K1 is less than K2. Suppose we fix any item, so K1 should be a less than K2, K2 should be a less than K3, and so on up to the K7. The key K1 is greater than all the keys in subtrees pointed to by C1 and less than all the keys in the subtree pointed to by C2. Similarly, this relation holds true for other keys also. Key C1, key of C1 is less than K1, or so K1 is less than key of C2, and so on up to the K4, K5, K6 and K7. We're talking about the K7, C7 children are less than the K7 and C8 values are the greater than the K7. By this structure, you usually understand how we go for to creating, generating a M-way search tree structure. One thing you should to note when you're forming a M-way search tree, the definition of a M-way search tree, we can say that M-way search trees are generalized because we form a hierarchical structure. That's why we used M-way search tree are generalized form of binary search trees, and a binary search tree can be considered as an M-way search trees of order 2. So this is you have to note that this point. I'm talking about now structure of M-way search tree. Here we taking one example. By this example, you can understand the concept, how we can design the structure of M-way search tree. Here we talking about take a simple example of order of 4. So M is equals to 4. So M-way, it means the name of the M. M is representing any integer value, that's a 4, and way is representing the producing a child. So it means 4 it will be given in a question. You can easily understand the maximum size, the maximum producing children are 4, and the maximum keys are the 3. As I told you, keys are always 1 less than the as compared to the child. So child is equals to 4. It means maximum keys are present in any position is called a 3. So in a root node, how maximum keys are presented are the 3. Minimum you can connect it 1 also. That is not any restriction in a M-way search tree, but it should be restriction in a B tree. So right now you can insert 3 keys because the order is 4. That's why we insert all 3 keys at a root node. Here you can see 50, 100 and 150 are the 3 items, and all items are available at the root node position also. But the system way, first we insert 50, then we insert 100, then we insert 150. We can't insert data at a runtime. We runtime we can insert, but it should be connected in a ascending way. Data would not follow any path. So 50, 100 and 150. If we're talking about the second level, all the items like 35 and 44. 35 and 45 both are the less value as compared to the key 1 value. Key 1 value is a 50 and 35, 45 are comes under the C1. C1 is the children of K1. Here the K1 value is 50 and 50 having a 2 children. One is a lesser child and say in a form of C1. One is a greater child is a form of a C2. So C1 childs are 35 and 44. We're talking about the second child which is are greater than the as compared to key 1 value. So the values are 85 and 95 and both are the greater than the 50. But 85 and 90 are also a lesser than the K2 value, and the K2 value here is 100. So you can check 85 and 95 both are the less than the K2 value, that is 100. So 85 and 95 are the greater to K1 value 50 and both are the less than the K2 value 100. And so on 125, 135 both are the greater than the 100 but both are the less than the 150. That should be connected in between the children of 100 and 150, or we can say the right successor of 100 or the left successor of 150. And the last one is a 175. 175 is greater than all the root node items. That's why 50, 100, 150. That's why it should be connected at the as a right child or the right successor of 150 in the form of 175. Talking about the second level, that is the 60 and 70, and 60 and 70 both are the greater than the 50. So we go for the right child of 50, and the right child of 50 is a 50 and in between the 100. So child are 85 and 95. 60 and 70 we can't insert both child at the same position because here we having a restriction of order of M. We can maximum of producing insert our item. So the maximum the key value is only 3. So we can't insert say 60 or 70 at the same position. So we can 60 and 70 we insert as a left child of 85. So we connected as a left form of a left successor of 85. Another is a 90 compared to the root node 50 it will be lie in, between 50 and 100. That's why I follow the path of second one, that is a case C2 children. C2 children already 85 and 95 available. We can insert it between the 90 also, in between 85 and 90. But it again depend on me. There is no any restriction to insert at that particular level. You have to go to insert at that time, but you can't be insert also. That thing is also available. You can generalize or you can improve or adding your data as data in a hierarchical form under to the level to level also. So there is no any restriction. So we can connected 90 in between the 85 and 90. So 95. So it should be as a right successor of 85 and left successor of 95. Next is a 110 and 120. Both are the greater than 100 but should be less than the 150. So it follow the path that is a C3, and the C3 is child is in between 100 K2 and K3. So the child already items are available in a form of 125 and 135. But both item 110 and 120 are less than the 125. It should be connected as a left successor or a left child of a 125. That should be connected in the form of as a left successor of 125, 110 and 120. Talking about the last item, that is a 75. 75 is greater than 50 but less than the 100. So should be follow the property of path of 85 and 95. Then again 75 is less than 85, then go for the left child, and the left child 60, 70 already available. We can insert 75 as a current neighbor of right neighbor of 70. We can should be inserted, but again depend on me. But again depend on me, either we connected, either we insert a new item as a child of that particular node. So again depend on me. But when this is an M-way tree, we can insert item either a neighbor or as a right child also. That again depend on me. So, but again in a M-way tree, you having a freedom to insert a node either a neighbor form or either a children form. So this is a way to representing a tree of a M-way search tree. If you see anywhere in a root node as compared to internal node also, or the, up to the leaf node, maximum keys are present in anywhere is a 3, maximum 3, but 2 also is supporting, 1 is also supporting, but more than 3 keys, it means more than internal nodes, more than 3 internal nodes are not available in this tree. If the anywhere, if you insert more than 3 keys somewhere, but which is not follow the property of M-way tree. So you have to have a restriction, that is a completely order of M. Up to the order of M, you produce, you can connected, you inserted a new item at the same level or at the same internal nodes. You can't insert it more than the order of M childrens. So here we are talking about the searching also, searching operation also. We can understand searching operation also, and we understand the concept of order of M, that is M equal to 5, that's tree. If M order of M is equals to 5, it means how many item, how many keys are, maximum keys are present in the root node at 4. Minimum 1 also, maximum 4 also. So that is completely depend on the order of M. Maximum producing child are 5 and the maximum keys are available in anywhere on any internal node or at a root node, that is only a 4. Not more than 4 keys will be available in anywhere in the tree. Suppose this is a tree of order of M equal to 5. So we having a root items like 18, 44, 76, 198. All items are connected in a ascending way order, and the maximum is we connected only of 4 items. That's why after that we, if any item should be request to connect it to insert here, we have to connect as a children format, not as a neighbor format. So the 7 and 12 both are the less than the 18. That's why we should be connected as a left child of 18. That is a C1 connected in the form of C1 connected. Next one is the 80, 92 and 141, and all are the greater than 18 as well as 44 as well as the 76. That's why we connected 80, 92, 141 as a right child of 76 as well as a left child of 198. Talking about the 262, 262 is greater than all the items are available at the root node. That's why you should connect it as a right child of 198. Talking about the 8 and 10, 8 and 10 are less than the 18, but it is greater than 7 and less than 12. So we connected 8 and 10 as a right child of 7, or we can say as a left child of 12. So in the same phenomena, 77 connected as a left child of 80, 148, 151, 172, 186, all are the greater than 76 and but less than the 110, 198, and should be connected in between the 76 and 198. Here we having already three items in a form of 80, 92 and 141, and this new items all are greater than the 141. That's why it should be connected as a right successor of 141. So all items are available as a right successor of 141. Talking about the next is 272, 286 and 350. All are greater than the 198 as well as the greater than the 262. That's why all items are connected as a right successor or right child of 262 in a form of 272, 286 and 350. All are the last children of this tree. So you can understand the concept of M-way. In no anywhere we can't insert at the root level as well as any internal node more than the 4 keys. So because the order of M is equals to 5, so maximum producing child of anywhere or the internal or root node is only a 5 children. That's why the internal keys having more maximum keys are the 4. Not more than 4 will be supported in anywhere inside the M-way search tree. So here you cross check. Maximum keys are available in everywhere is a 4. This is a concept of order of M-way search tree. By this tree, you can perform various type of operation like insertion, deletion, searching. So first we go for the simple operation that is called the searching. The operation is given you, go in M-way search tree and search a 77. So first you go for the first item, root item, and at a root position you having 4 items in a form of 18, 44, 76 and 198. So here we searching item is 77. So first we fix the pointer at the first position, that is 18. Here we cross check if a new item is equal to 18 or not. So is not equal to 18, no, go for the if and else condition. The new item is greater than or less than. So finally we get 77 is greater than 18. So next pointer will be fixed to the second position, that is a neighbor of 18, that is the 44. Again we cross verify, again we having a result, new item is greater than 44. Again our pointer will be shifted to the current right neighbor of 44, that is in form of 76. Again we check 76 is not there, equal to 77. But so again we cross check. So again cross check, the next item is 198. So it means 77 should be lie in between the 76 and 198 is a form of a child of a 76 and 198. So we follow the path of that particular right successor of 76, or we can say the left successor of 198. So next generation is already items are available 80, 92 and 141. One by one our pointer will be fixed at the first position, that is 80. So 77 is less than 80, so we can't go for the neighbor part. We find out the left neighbor because here no one is available in the form of left neighbor. So we go for the as a left child of 80. So if we got the left child, that is a 77. So we comparing to the new item with that particular item. Both items are matched. It means our searching operation is successful. So by this one, you can search your item one by one in a complete tree, in a whole tree. Suppose I want to search at 286. Again we comparing starting with the root item, that is called 18, 44, 76, 198. So 286 is greater than all the compared to the root items. That's why we follow the path of the right subtree of 198. As a right subtree of 198 is our 262. So again we compare 286 with 262. Again 286 is greater than 262. That's why we follow the property, follow the path of the as a right successor of 262. Here we having 3 items, 272, 286 and 350. One by one we cross check by the pointer. So new item, our searching item is 286. First we check with 272 is not matching, then pointer will be shifted to the second neighbor of 272, that is a 286. Now here our item will be matched with the present item, so we can say our search is successful. So if item is available inside the M-way tree, so definitely the operation is successful. If item is not available in the M-way search tree, the result will be shown as an unsuccessful case. So by this concept, you can search your item in a M-way search tree in a minimum time and a less time as compared to the binary search tree. So you understand the concept of how we searching an item inside the M-way search tree. This is a one operation. we can perform to searching an item in a M-way search tree. So in this tutorial, we understand the concept of M-way search tree, why we require this M-way search tree, what is the drawback of binary search tree, what is the not as a drawback, we can say what is the limitation of binary search tree. That limitation will be sorted by the M-way search tree. Again, M-way search tree which will give you the smooth way of searching, insertion and deletion of data, and also there's an updating version of the binary search tree. All the operation you can perform in this tree in a smoothly way in a less time as compared to the binary search tree. So today in this tutorial we understand the concept of definition of M-way search tree, the structure of M-way search tree, and also we understand the searching operation in a M-way search tree. In the next tutorial we having two remaining operations like insertion and deletion that will be continuing in the next class. We understand the concept how we insert a new item in a M-way search tree and how we delete an item from a M-way search tree. Two operations will be remaining that will be covered in the next tutorial. So for this tutorial, thank you.